Hi, and welcome back to today's lesson. Today we're looking at the application of the equilibrium constant for different types of reactions. So if we have a look here, the syllabus outcome is to explore the use of KEQ for different types of reactions, including but not limited to the dissociation of ionic substances or solutions and the dissociation of acids and bases. So we can actually use that equilibrium constant for different types of reactions and can calculate the KEQ for each one of those. So we're going to investigate today the dissociation of the ionic substances and also the dissociation of acids and bases. Now the reason, we're only going to touch on those, and the reason for that is that the dissociation of ionic substances is going to be covered in more depth in inquiry question 4 of this module, and the dissociation of acids and bases is going to be covered in significant depth in our acids and bases, which is module number 6. So earlier in year 11 we did cover precipitation reactions, and that's when we have our two aqueous solutions mixed together in a vessel and we're producing a precipitate, which is an insoluble solid forming in our test tube. So when we do that, we were writing some ionic equations that were representative of the reactions that we were studying. So let's use the example that's on the board here, and we've got potassium iodide with lead nitrate reacting and producing potassium iodide, and our potassium nitrate. So in year 11 we discussed precipitation reactions, and in a precipitate reaction, we have two substances in the aqueous form placed into a vessel and they produce a precipitate, which is an insoluble solid forming. So when we do these reactions, we can write them in their ionic form, because when we place these things into solution, they're able to dissociate, and this means they're free then to move around. So when we pop the potassium iodide into solution, they dissociate into their ions of potassium ions and iodide ions. So in the equation that we have below, you can see here we've written the equation out into each of their ions there. You will notice, however, the lead iodide is not broken up into its ions because it is the precipitate that is formed, and it's there in the solid form. So looking at this equation that we've got, we have got our potassium on both sides of the equation, we've got our nitrates on both sides of the equation, and they are spectator ions. So what we're left with then is our lead ions and our iodide ions forming our lead iodide solid. So when we do this, we can write an equilibrium constant for this dissociation, and if we think of this reaction in this form, I have it dissociating here in that I have got, say for example, my solid or my precipitate that's formed, and it dissociates into the positive ions and the negative ions. And these reactions are usually reversible, so we can see that indicative below with the reversible sign there. So if I was to look at that KEQ, I have got my reactants, which is AB, so that is on the bottom, and the concentration of my products on the top, the A plus and the B minus. And we can apply that for this equation below. So when I pop into the KEQ for this precipitation reaction or the dissociation of ionic substances, we can write that with our lead iodide in the equation, but because we know that solids, when we have aqueous solutions and then we have solids, we don't include the solids in our equation. And so when we do that, we are simply left with our KEQ being the concentration of lead ions and the concentration of iodide ions. Now let's see if you can pick up my mistake there, because there is one in the KEQ formula. We'll talk about that tomorrow in class. So we can also apply the similar knowledge to the dissociation of acids and our bases. So it's important that we briefly look at our acids, and this is probably the only time that acids have come into our equilibrium and acid reactions, so let's make the most of it. here we have our acids, and when we have our acids, they form our hydrogen ions. So all our acids will have the hydrogen in them. And when I put them into solution, they will form those hydrogen ions in that solution. And so when I put those acids into solution, they again will dissociate into their ions. So we can calculate an equilibrium expression or write an equilibrium expression for the dissociation of these acids. And when we do so, we tend to give this another name, which is our acidity constant or our acid dissociation constant, and given the symbol Ka. But the way we calculate that is the same as if we were calculating the Keq. And this Ka is a measure of the strength of acids, and we will discuss this more in our next module. So if we have a look at these two acids that are here, hydrochloric acid and sulfuric acid are both strong acids, and the reason that they are strong acids is because they completely dissociate in aqueous solution. So they go to completion and totally dissociate into their ions. So because it goes to completion, it's not an equilibrium reaction. So if I was to calculate the Ka for this, it would be really, really large because my products have 100% dissociation, so that number would be quite large. Our sulfuric acid is considered, and we will discuss this in our next module a little bit further, is a diprotic acid. And what that means is when it dissociates, it forms 2 hydrogen ions. And again, if we were to calculate this Ka, it would be very, very large because the products go to completion, so the concentration of both those ions would be high. But most acids don't go to completion, and they do form an equilibrium, and those ones are called weak acids. So if I look at the dissociation of acids, we can write that in a general form where we have Ha, H being the hydrogen ions and A being the anion associated with that acid. For example, here we have acetic acid. So we have CH3COOH in solution, and it dissociates and forms the anion, which is CH3COO -1, and our hydrogen ions. So if I was to write that in the equilibrium constant, and because it's an acid, we call it Ka, you'll see that the process is the same. CH3COO negative concentration, and the concentration of the hydrogen ions over the initial acid that had dissociated. Now, if you have a look here at the value, it's 4.2 times 10 to the -7, so it's quite a small number. And weak acids have a small Ka. Now our Ka can vary from acid to acid, but the less it dissociates, the smaller the Ka, so the weaker the acid. Now we can apply a similar principle to our dissociation of bases. Our bases also will dissolve in water to form an equilibrium constant. Now our strong bases are usually hydroxides of the group 1 metals. So our sodium hydroxide, lithium hydroxide, and so forth. If the Kb is high, again, it means it's dissociating almost completely. If our Kb is quite low, that means it is not dissociating as much there, and it's a weaker base. The smaller the number, the weaker the base. So you can see here we have a base, add it to water, and then I'm getting my ions with our hydroxide. So again, that Kb is a measure of the strength of the base. We will discuss this further in our next module. But let's look at this example that we have here. Ammonia is an example of a weak base, so I have ammonia, I'm adding it to water. And when it does that, one of the hydrogen ions from the water attaches to the NH3, and it's becoming NH4 and plus because it's gained a positive charge from that hydrogen ion. And then we're left with the OH, which is a -1 charge. And again, we can calculate the equilibrium constant in the same way that we have calculated the equilibrium constants before. And we can see here that I have not included the water. Now you should be able to tell me why that is from our previous lessons.